Welcome everyone. The next speaker is Ernesto Lupercio from Cinvestav, Mexico. He will be speaking about quantum toric geometry, first session of the Minicourse. Go ahead, Ernesto.
Thank you so much. Thank you so much. I'm happy to be here. I do apologize to the super experts because this is a mini course, so I'll be fairly elementary, especially in this first lecture. But I'll try to say where we are going at and try to build connections. My talks are related to every other talk that has occurred at the conference so far. I'll try to stress on the connections. And just to connect to the previous talk, Misha in his fantastic talk explained how there is this formal irrational geometry going into irrational directions. And here, what we're going to do is we're going to construct the actual geometric objects that should degenerate to these more formal tropical objects that we were seeing in the last talk. In any case, this is an IMSA event, I repeat, and the Institute for the Mathematical Sciences of the Americas is an institution highly supported by the Simons Foundation, and one of its objectives is to connect mathematicians in all of the Americas and Latin America to the world via the very natural setting of Miami. So here we're all virtually in Miami, even if I'm 1 hour earlier. Okay. So irrational fans, well, this is an irrational fan. I thought it was a fantastic name for this conference, the concept of irrational fan. But we're going to refine this concept of irrational fan into the concept of quantum fan. That it's almost an irrational fan, but with a little bit more information. Okay, so for the students, we're going to base our these mini course in 3 papers. The first one is the 2014 paper called The Definition of a Noncommutative Toric Variety, 2014. And here, these quantum toric stacks are first defined. So these are the irrational toric varieties or quantum toric stacks, where this, even in the rational ones, where these irrational tropical curves would live inside the actual geometric objects. So this is a more general paper that it's easier to read. Then this is also a paper that I recommend to the students. This will appear, but it's already on the archive, will appear in the notices of the AMS in January. And it's called Noncommutative Geometry Indomitable. And I also introduce all these basic things that we require to understand the motivation and setting for, and I say a little bit about quantum toric geometry in this paper. Noncommutative geometry indomitable, and it will appear in the notices of the AMS in January, but it's already on the archive. And the third paper that I asked the students to check is called Quantum Noncommutative Toric Geometry Foundations. It's on the archive, submitted for publication. It's this is the one, and this is now it has every technical detail you want. The previous 2 is to understand why you would be doing this and what would be the main ideas. And then in this one, you'll be able to see every technical detail. And now you'll be able to work with quantum toric space, varieties, manifolds, whatever you want to call them, stacks. After you read this, that has all the foundational details. Okay, so let me just remind you that a toric variety, say a complex toric variety, well, rather than the real torus, you consider the complex torus. This is the complex version of the circle. Is C star, is C minus a point. This is C star. Yeah, it's here. Is C, and then I take the origin out. And then this is the torus, is a corsally group and complex, moreover. And an equivariant, this is a scalar manifold, of course. And an equivariant compactification that means scalar. That's what a complex toric variety, you can think of a complex toric variety of this. Of course, there is toric varieties that are non-compact, but for the moment, let me just say this. Have this in mind, and then we're working only over the complex fields. The basic structure of a compact toric variety over the complex numbers, well, the CP1 is the complex projective line or Riemann sphere. Is a canonical example. The so-called moment map is in this case this mu, and it's just the height function. And this height function, well, the point is that the inverse image of nearly every point is a circle. And of course, there is 2 points where the inverse image is a point, the 2 poles. And well, a circle is a one-dimensional real torus. So
very well. Anyway, what I was just saying is that we have the complex torus, and this C star is just the complex version of the circle, and this is not only a Lie group, but it's also a complex manifold, and moreover a scalar manifold. And so we will think of a toric variety just schematically, just to fix our ideas, as an equivariant scalar compactification of the torus. So the torus is non-compact. This is not the real torus, it's the complex torus. So it needs to be, so it could possibly be compactified, and it can be compactified in many ways. This is not the one-point compactification. For example, here we have C star is the complex torus, and this is the same as the sphere minus 2 points. The sphere minus 2 points. And we compactified where we can add these 2 points. This is an equivariant compactification of the one complex dimensional complex torus. The C star contains the circle, that is the one complex dimensional, one real dimensional real torus. And the moment map, what does the moment map does? Well, the moment map, in this case, is just the height function for the sphere. And this height function, well, for nearly every point, the inverse image of this height function is just a circle. For nearly every point in the interval, certainly, open interval, it's a circle. And then there is 2 exceptions, of course, the North Pole and the South Pole. But the North Pole and the South Pole, I think of them as 0-dimensional tori. They are points. And then what the moment map affords is that it makes the sphere to be the disjoint union of tori. Nearly all of them are one-dimensional real tori. And then there is 2 exceptions. There are 0-dimensional points or tori. So CP1, well, the complex projective line or the Riemann sphere is a toric variety, and this moment map makes it the union of various dimensions, of tori of various dimensions. So here, let me just erase all marks and do them again. So here is a moment map in dimension 2. This is dimension 2. So this is R2. And this is X of complex dimension 2. This is an object that is meant to have complex dimension equals to 2. It's as a two-folds. And this is the moment map. Now, if I am in this two-dimensional facet, the interior of the, now it turns out that the image of the moment map, as we know, for a toric variety, and this is the theorem of Atiyah, Guillemin, and Sternberg, mentioned yesterday in Elisa's talk. This moment map, well, is a polytope inside, well, in this case, R2, Rn in general. And the inverse image of this point, the important point for me is that the inverse image of this point is a torus. It is two-dimensional real torus. But if I took the inverse image of this point, I would get a one-dimensional real torus, a circle. And if I took the inverse image of this point, I would get just a point, a let me call that a zero-dimensional torus, real torus. And again, the toric variety is realized thanks to the moment map as the disjoint union of real tori of various dimensions. Of zero dimension, of one dimension, most points actually of dimension 2. Most points will be all these Lagrangian tori of dimension 2, making up the toric variety. Okay, so the toric variety is decomposed into tori, and it also has famously, of course, well, the action of a torus, but if of a complex torus, because it is the compactification of a two-dimensional complex torus in this example. So there is a whole bunch of tori in these toric varieties, and this is the situation that we encounter here. This is the classical situation, and in the classical situation, the polytope, this polytope, actually I should have said that lands on Qn or on Q2. Actually, I should have said that lands on Q. It's a rational polytope. This is the classical situation. How does quantizing this situation look? Well, to all these real complex tori, to the complex tori, quantum toric variety will be the compactification of a complex quantum torus. The inverse image of the polytope, well, will become an irrational polytope. And this is a situation that was described very nicely by Prato on the first talk and by Fiammetta on the second talk. This is the situation, you know, this is an irrational polytope. We are going to go, they were interpreting this as some sort of generalization of an orbifold, a quasi-fold, but we will interpret this as a stack. Why? Well, because we want to have some morphisms, and we want to be able to do the modular space, and we want to be able to use all the technology that has been developed for the study of these stacks, and for other reasons that I will explain hopefully today. In any case, if I get a point inside this polytope, the inverse image will be a real quantum torus. A real quantum torus. And now this is a possibly irrational polytope. And actually, we will also not only work with polytopes. Well, if you are familiar with this, and I recommend you to check it before the next talk of this Minicourse, we're actually going to work with the more general case of fans. They were working more or less in the symplectic world. That is a way to think about it. And this is more in the algebraic geometric world. Our point of view is more on the algebraic geometric world. As Frank mentioned yesterday, well, all points of view are welcome in certain kinds of problems, depending on your problem. Okay, so we have this generalization where we replace the classical torus by a quantum torus. We replace all the classical tori that I mentioned in the previous slides. All these classical tori will be replaced by quantum tori. I haven't told you what is a quantum torus. But I will tell you what is a quantum torus. Okay, and once we do that, we will achieve a situation where now we want to consider this modular space of these objects. Because they are these stacks that we chose, well, then we are able to construct this modular space. And think of the modular space of curves, if you're familiar with that, and it's also related to what Misha was saying in the previous talk. The modular space of curves usually has two subindices. It has the subindex G and the subindex N. This is getting harder, but oh, no, I went back. It has the subindex G and the subindex N. And well, now we also have the subindex G. The subindex G in the modular space of curves was the number of mark points. And now the subindex G in our modular space is going to be the combinatorial type of the quantum fan. Just the combinatorial type that, well, in the classical case, it was the genus, sorry. That it was kind of the combinatorial type of your Riemann surface. In our case, G is going to, the genus, think of the genus of this quantum toric variety or toric variety as the combinatorial type of its fan. It's a combinatorial type that determines, say, the basic topological features of your toric variety, just as the genus determines the combinatorial type. The combinatorial type, the genus, determines the main topological features of your Riemann surface. Following this analogy, rather than having mark points on the surface itself, like in the classical case, now we're going to have some mark points on the fan, and this is going to give us a mark gerb. This is going to give us a gerb structure, and this produces this modular space. So we will have this modular space. Let's see if this works. Pen. We will have this modular space. And this modular space is kind of nice in that the modular space, this modular space of toric varieties now, quantum and not quantum, the rational points of this modular space, the rational points are the classical toric varieties with the classical tori, everything we saw before. But now you have a bunch of irrational points on this modular space. And this modular space has the characteristic that is a complex orbifold. So it's it's just a complex or classical, not quantum, not non-commutative, nothing. This is just a complex orbifold whose rational points are the classical toric varieties that you were familiar with. And in fact, these most singular points tend to be the smooth ones, and all the other ones tend to be just the orbifold ones, the classical toric orbifolds. And then there is the irrational points, and the irrational points correspond to the quantum toric varieties. So that. But because this is a mini course, I will try to explain now a lot of this will happen on next talk. I will talk about this on next talk. Although Mr. Boava will speak about it on next on the talk immediately after this one. But I'm going to go back now and go back to trying to explain what is a non-commutative space and a stack and these things that will be my objects. My quantum toric varieties will be non-commutative spaces and will be stacks. So I will try to explain now what I mean by these concepts in this mini course. But of course, I warn you that I will take, this talk will end 10 minutes later because of my technical difficulties. Okay, so let's try to understand what is a non-commutative space. And we do that by going back to Gelfand duality. So what is Gelfand duality? Well, if you get the category of all spaces, say Hausdorff compact topological spaces, and then you take the category of algebras, commutative C-star algebras. These categories are essentially the same. They may look very different. One looks like topological spaces and the other look like algebras. But it's you know how to go from one to the other. Given a topological space, you construct its algebra of continuous complex valued functions. Continuous is important. This is the topological structure to define the structure of the algebra. And it's an algebra because it has pointwise multiplication. So, well, they are not the same algebra in that one is the opposite of the other. This functor is contravariant. If I have a continuous map of spaces, well, the map of algebras goes the other way around. So this is what the op means. This is what the op means. So the spaces is equivalent to algebras op. So they are the same category. In classical algebraic geometry, you can start with an affine variety, and one can produce a commutative algebra O of X by taking its regular functions. And then you can go back to X. I obtain an algebra, but can I go back to X from the algebra? Well, of course, you can take the spectrum of maximal ideals, and then you can go back to X. Well, there is also, if you take this category of continuous complex of C-star algebras, commutative C-star algebras, blah, blah, you can also go back with a spectrum construction. It's a little bit more subtle because they are not algebraic, but it's the same idea. So you can go back and forth. So it's the same thing to have spaces as to have algebras. And some people might think this is rather perverse, but some people might think this is very useful. And we welcome all perspectives. So just to fix the ideas, on a usual manifold, you have local coordinates, x1, x2, xn, and you have the commutativity in the coordinates, x1, xj is xj, xi. Think fancifully, if you want, that on a non-commutative manifold, the whole point is that the local coordinates no longer commute. The local coordinates, just think that formally that the local coordinates no longer commute, and you'll be okay. In fact, Misha defined the non-commutative torus just by defining some coordinates that don't commute. And then he said, we have the non-commutative torus, a non-commutative space, just by defining a non-commutative algebra that is meant to be its algebra of functions. So, so this is the usual torus. The usual torus, you have this coordinate x, it's a periodic coordinate, and this coordinate y, it's a periodic coordinate. And then, well, traditionally in the usual torus, xy is yx, just the usual torus commutes. In the non-commutative torus, coordinates don't quite commute. They almost commute because I am meant to think that h bar is a very small real number. In fact, this number appeared, this equation even appeared in a very experimental thing in classical quantum mechanics. These are in Lie algebra form, they are the Born, Heisenberg, Jacobi, I believe, relations. In any case, geometrically, what you are to think is that now the coordinates don't quite commute, but they fail commute by a little bit. And this is the little bit that is making them not quite commute, that little unitary complex number, when you try to switch x and y. So, in geometry, where are non-commutative spaces coming from? Well, very often they come from bad quotient spaces. Bad quotient spaces already appear in Elisa's talk. A perfectly good topological Hausdorff space can have a non-Hausdorff quotient. Very often this occurs if you have a very nice topological space and you divide by a group that is not compact. This is a source of many examples. And yeah, I said it here. M mod G with G non-compact. Let me try to keep track of my notation. So, and very important, fundamental, perhaps the fundamental example for all this theory of quantum toric geometry is the Kronecker foliation. So what is the Kronecker foliation? You just take R2, the plane, and then you take Z2, the integral lattice, and then you take this foliation made of all parallel lines of the same slope. All these parallel lines of the same slope, and we're going to make the slope to be h bar. We're going to make the slope to be h bar. Okay, so when you now take the quotient by this lattice, and what you get is you get the Kronecker foliation. This is the Kronecker foliation, and it's a very nice foliation on T2, because R2 descended to the two-dimensional real torus when I divided by the action of Z mod 2. But also all these red lines descended to lips of a foliation. And of course, now we get the dichotomy. Rational, irrational, that we have been getting all along this conference. If the slope is rational, the slope h bar of the straight lines is rational, well, then this is a foliation by torus knots, and every leaf is compact and is diffeomorphic to a circle inside the torus. But when h bar is irrational, every leaf is diffeomorphic to R2 and immerse R2 into the torus. But every leaf, in the irrational case, every leaf is every leaf of the foliation is dense in the whole torus. So every leaf of the foliation is dense in the whole torus. Okay, so that's very nice. And now, well, this is what I said for rational slopes exercise, students. The quotient is Hausdorff, and moreover, it's a circle. For irrational slopes, the quotient is not Hausdorff, and is no longer a manifold. It's non-Hausdorff. The quotient is, try to imagine the quotient of T2 by this action of the reals that comes from an irrational slope, and you'll realize that it's a non-Hausdorff topological space. It's bad. But we can profit from thinking of this second quotient. Elisa was thinking of it as a quasifold, and we will think of it as a non-commutative space. And this is an idea of Alan Kohn. Okay. Well, we will need all along in the development of this theory groupoids. And these are objects that generalize group actions and generalize groups. A group can be thought as a group action if you let it act on a point. This is a group as a group action. Every group acts on a point, why not? And every group action is a groupoid. Let me just tell you, well, I will assume that you know what is a category, but my point in writing it down is that I will use two maps, the source and the target. So given an arrow of the category, the source of this arrow is X, and the target of this arrow is Y. And see, this is my notation for the maps in a category, the composition, etc. Okay, so that's a category. And now we have well, I will start skipping a little bit the situation. Composition is associative. The composition of arrows, if I have an arrow in a category and an arrow in a category, an arrow in a category, well, all this diagram going this and this is this, and all this diagram is commutative, and this diagram looks like a tetrahedron. That's the associativity of composition in a category. And this is important for us. Our motivation will be the nerve of an open cover. If you have a topological space and you form a category where the objects are the open sets of the cover, you put an object for every open set, an object for another open set, an object for another open set, an object for another open set. These are the objects. And then arrows, well, you put an arrow whenever there is an intersection of these open sets, in every direction, the arrow, if you want. Two arrows, but anyway, an arrow. Then you get that these are diagrams in a category. And if the diagram commutes, you are meant to think that it fills up this triangle. So whenever three open sets have an actual intersection, then you fill this out. Here you have four open sets with an intersection, and then you have a tetrahedron, because of what I said before, and then you are supposed to fill it out. And then this forms the nerve of an open cover, coming from the category of open sets on a topological space. Okay. So what is a functor? Well, I will assume that you know what is a functor, but this will be my notation for functors. The important thing is that a functor sends objects to objects and arrows to arrows, and then that it does this, that it preserves composition. And internally, inside the category, you can define that an arrow has an inverse. My point is that categories, you are used to thinking of categories, perhaps as students, as categories of, I don't know, vector spaces, groups, sets, like this category. categories of objects that are sets. But it doesn't need to be the case. The objects could be, you can think of a category just like you think of a group as an abstract thing that just has objects that are abstract things and arrows that are abstract things, and categories will be generalizations of monoids or of groups, and they will reflect some symmetries. While groups reflects global symmetries, say of a space, categories and groupoids that are just certain kind of categories reflect symmetries that may be only local. They don't need to be global symmetries. So I am inviting you to think of a group category as a generalization of a group. I'm inviting you to think of a category as a generalization of a group. If a group, you think of a group as acting on a point, this is the object. Well, in a category, you think that these are kind of local symmetries. You think that the arrows are local symmetries. Okay, now, categories have, as I said, functors. A functor can go from one category to the other. And functors, in turn, have natural transformations. And I'm inviting you to think of a natural transformation of functors as homotopies between them. So the invitation is to think of natural transformation of functors as homotopies. And this can be done formally, and is done in the papers that I mentioned at the beginning of the talk. But a definition of a natural transformation that may be not entirely standard to you is a natural transformation from a functor to another functor is a homotopy, where I is this category. And so you can think of natural transformation as homotopies, and you can think, therefore, as equivalence of categories as homotopies of between categories. So I'm inviting you to think of equivalence of categories as homotopies between categories, homotopy equivalences. This not only makes formal sense, it can be made rigorous, but additionally, it makes intuitive sense, because often an equivalence between two categories is achieved by fattening it up and then skinning, making it thinner, thinning it out. So you start with a category, you can add objects that are isomorphic to objects that were in this category to get a new fatter category. And then you can take away objects, even original objects that were in A. You can end up with a category B that has no object in common with A, yet is homotopy equivalent. Or simply equivalent categories. So if you think in terms of spaces, well, suppose that you have this space C, and then you have this space A, and then you have this space B, and then C is, suppose that it has a retract to A and a retract to B. Then, well, of course, A will be homotopy equivalent to B, although it will be hard to construct a map from A to B, an explicit map. But because of the existence of C, you will have an equivalence between A and B. So this is how two equivalent categories may look like. They may not have objects in common. This equivalence of categories will be very important, extremely important for us. Okay, so Well, there is categories. The only categories that we're really interested in for the theory of quantum toric varieties is groupoids. And what are groupoids? There are categories where every arrow under the world has an inverse arrow that well, if I compose this, then it gives me one identity, and then if I compose them in the other direction, it gives me the other identity, you know? So they are called groupoids because they generalize groups, as I already said. So a group can be thought as a groupoid by considering the category that has one object and has an arrow for every element of the group. And then you can think of a group as a groupoid. And of course, groupoids generalize groups, but you think of groupoids as sets of local symmetries, while you think as groups as sets of global symmetries. So you are thinking of these, I'm inviting you to think of these as local symmetries. And I'm inviting you to think of groups as global symmetries. My transparencies and the 3 papers are on the web. Okay, so don't worry if I'm going a bit fast. For example, every equivalence relation, this is an important example for us. An equivalence relation can be made into a groupoid. How? Well, the objects of the groupoid are the set that we want to impose the equivalence relation, and the arrows are simply the pairs that belong to the relation. And this is the composition law. With this composition law, this becomes a category, and moreover, it becomes a groupoid. And I am extremely interested in understanding if I have a groupoid and I have another groupoid, what those 2 groupoids that are homotopy equivalent in the sense of categories look like. They may be having completely different objects, you know, but then they should represent the same thing. So I want with groupoids up to homotopy. And groupoids, when I work with groupoids up to homotopy, those are called stacks. Group actions also produce groupoids. Let me just say that sentence here. Groupoids up to homotopy are stacks. And I'm going to work with stacks. Quantum toric varieties will be stacks. Okay. Now, every group action also produces a groupoid, the translation groupoid. The objects of this groupoid are the points on your manifold, say, and the arrows are pairs M, G. These are the arrows that goes from M to G dot M. And this is a typical arrow in this groupoid, and this is the composition of arrows. And this is GMH. And this is the composition of arrows, MHG. That's how the typical commutative diagram looks in this groupoid. These are important groupoids for us, very important. So every group action produces a groupoid, but I want to be able to change the homotopy type of this groupoid. Well, there is more structure, of course, that I have to impose into all these. We want to, I've been totally formal up to now, but I want the objects of my groupoids to be a manifold, to be a set and to be a manifold. I want the arrows of my groupoid to be a manifold, the set of arrows, all the arrows of, in the previous example, this is true. In the previous example, the objects of my groupoid is a manifold for a group action on a manifold. And the arrows, if G is a Lie group, can be made into a manifold. I need to ask that G is a Lie group. So a Lie group acting on a manifold delivers you a Lie groupoid. So a Lie groupoid is one that well, it's a groupoid, but this is a manifold, this is a manifold, and all the structure maps are smooth. I also have the continuous version, all these versions, but I will think of the Lie groupoids in this talk. And I want to understand the homotopy type of, now really, C infinity stacks will be Lie groupoids up to homotopy. But this homotopy that I'm calling it homotopy because it is a homotopy, people call this homotopy, call it Morita equivalence. So they call it that for historical reasons. I can impose even more structure. I can think of ethyl groupoids. I also will use these ones. But the important thing is that any manifolds with an atlas, the pair of a manifold and an atlas gives you a Lie groupoid. I have to fix an atlas to get one Lie groupoid. The objects of this Lie groupoid, are pairs M, I, where M belongs to UI. These are the objects of this Lie groupoid. The arrows of this Lie groupoid, the morphisms of this Lie groupoid are triples, Mij, where M belongs to UI, Uj. This is a typical arrow in this Lie groupoid. And this is a manifold. This is a manifold. It is a Lie groupoid. And these are smooth maps. And this is the composition law. So an atlas produces a Lie groupoid. And the following is true. Theorem, exercise for the students, exercise for the students. Two Lie groupoids of this kind, if I give an atlas and another atlas, are homotopy equivalent if and only if the atlases are equivalent as atlases. Namely, if and only if they have a common refinement. So the equivalence class, the homotopy equivalence class of atlases is the same as a smooth manifold. It's the same to have a smooth manifold as to have the homotopy class of atlases groupoids. Okay, so, well, this is because I gave you what it was a homotopy equivalence of categories. This is the same, but in the smooth case. And it's called, as I said before, Morita equivalence. Morita equivalence is just the homotopy equivalence that I described before, but written down in the smooth category. And what I already said is that if we have two Lie groupoids, they are Morita equivalent if there exists, well, the same situation, one that fattens it up and then thins it out. We will call it a GG by bundle, because this is, you can think of it as bundles. You can think of it as a bundle over G prime. So this is fatter and this is fatter. And then it thins out in two different ways. And then this is the homotopy type of groupoids. And the equivalence class is called the stack associated to the groupoid. A stack could have many groupoids associated to it, just as a manifold could have many atlases associated to it. As an example, given a smooth manifold and two atlases, the two associated groupoids are Morita equivalent if and only if the atlases have a common refinement. And then the Morita equivalence class of any one of those two groupoids is the same as having the smooth manifolds. So C infinity stacks generalize manifolds. And they have nice morphisms. C infinity stacks have nice morphisms. They unfortunately do not coincide with the morphisms of quasifolds. In any case, stacks can be associated to, I'll finish in this talk in 4 minutes. Stacks can be associated to foliations. How? Well, if you give me a foliation, think of the Kronecker foliation. Think of the Kronecker foliation, la 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 la. Then you take the holonomy of this foliation. It was h bar. And for the Kronecker foliation, it was the rotation of h bar on the circle. This was the holonomy. This was the holonomy. So you take the holonomy. So this holonomy groupoid, this Z acting on S1, this group action was the holonomy group action on the Kronecker foliation, and H is the holonomy groupoid given by this group action. Well, you can do it in general, not only for the Kronecker foliation. And the holonomy groupoid is always Morita equivalent to some étal groupoid. So this gives you an enormous factory of stacks of étal groupoids, and then you can form the stack associated to that groupoid. And these stacks, this will be the stack associated to a foliation. But notice that many groupoids and many foliations could give you the same stack. This is treated at length in the book by Ike Murdak and Mershun, or whatever it's pronounced, I'm sorry, Introduction to Foliations and Lie Groupoids. Very nice book, I recommend it. So now to every groupoid, to every stack, I get one of these groupoids, and I can associate a non-commutative algebra. So I can associate a non-commutative algebra by this formula. You just give me the elements of this algebra are complex valued functions on the manifold of objects, manifold of arrows. There are complex valued objects on the manifold of arrows. And well, we can give them this product that uses all the commutative triangles in the category. We add over all these commutative triangles. So to get F times G at alpha, we add over all these commutative, over all these factorizations in the groupoid, in the category. And this gives me a non-commutative algebra. It's called the convolution algebra of the groupoid. Now, it seems to depend on the groupoid. In particular, for a group, it just gives you the group algebra. For the equivalence relation that relates everything to everything, it just gives you the matrix algebra. This is a groupoid. that relates everything to everything. And then it gives you the matrix algebra. Well, the whole point is that if you have groupoids and functors and natural transformations homotopies, Morita equivalences, they are sent by this convolution. Now we apply convolution. And then we get associative, possibly non-commutative algebras, bimodules over the algebras, and bimodule morphisms. And well, this means that this is the category of algebras that we have to consider. This is the category of algebras that we have to consider, of non-commutative algebras. And well, this is all to say that the right notion of isomorphism of algebra may look funny, but it's called Morita equivalence of algebras, and it's not what you would think at first. Now you need two bimodules, and then we say, well, the two algebras are Morita equivalents if they satisfy this complicated definition. But anyway, this gives me that I can go from groupoids to non-commutative algebras. Now I'll skip the examples. And well, I will finish with this diagram. I can go via convolution from groupoids to non-commutative algebras, and via homotopy equivalence from groupoids to stacks. And if I define non-commutative spaces as non-commutative algebras modulo Morita equivalence, then this gives me a map from stacks to non-commutative spaces. And because quantum toric manifolds will be stacks, they are stacks, then this will give me quantum toric non-commutative spaces. Non-commutative spaces. So, so let me finish today at this point. This tells me more or less what are where my quantum manifolds, quantum toric manifolds will live. They live here, and they therefore produce non-commutative toric manifolds. They produce these non-commutative spaces. And they will be generalizations of the Kronecker foliation. Which generalizations of the Kronecker foliation? Well, LBM theory, LBM manifolds, with their foliations, with their canonical foliations, will be the ones that will give me these stacks. So I will use these foliations that were described by Alberto Verjovsky in his talk to produce the stacks, and then therefore the non-commutative spaces that represent quantum toric non-commutative spaces. But that will be on my next talk. Do you have any questions? Well, I don't think we have any questions, so we can have a 5-minute break before the next talk. Thank you so much.